Hello, how are you? Let's talk about the pendulum, right? And what we can conclude from your investigation, our investigation, my kids, of a pendulum. All right, I've picked three instances in this pendulum's motion, and we want to look at each of these instances and analyze what's going on in terms of, well, for us, energy. All right, and so if we look at this instant number one at the top, I am not, well, bar charts aren't the most scientific of tools, but in this context, it'll show us what we want to see. And so at the top, well, what kinds of energy does this pendulum have, or the pendulum bob, I guess? Well, at the top, one thing we know is that this thing is not moving instantaneously. All right? And that means that if we look at kinetic energy, well, there's none. There's our little zero height bar. All right? However, at this place, regardless of where we call height zero, and in most cases, it's the most convenient to call height zero the bottom of the pendulum swing. So let's just go ahead and do that. Let's define this as height zero, and that's a big deal in this part of the unit. You can decide where you want to call height zero. It will never make a difference in your answers. Well, I shouldn't say that. Yeah. If a height zero is not defined for you, you can choose one for yourself. I'll just leave it at that. Okay, so, at the top, well, here's height at the top. And therefore, this thing has some gravitational potential energy, mgh, that let's arbitrarily say is, I don't know, that much. And so we can do a little bar for GPE that looks like that. Yeah? And then we could also look at mechanical energy, which is the sum of kinetic and gravitational potential energies. And at the top, there's no GPE. I'm sorry. There's no kinetic energy. There's some arbitrary here amount of gravitational potential energy, and therefore the mechanical energy is just the same as the GPE. It looks taller. Come on. Good. Yeah, good. Now, this thing swings to the bottom. Well, what happens? Let me try to do this. Is that going to work? Yeah. Oh, okay. Okay, that's over here. Well, now we know, for example, that it's at the bottom at what we've defined to be height zero. So now there's zero GPE. But we now know that this thing is moving. Oh boy. Sorry, folks. Oh boy. Sure, height zero. Good. It's now moving this way with a speed v, its maximum speed. And so how much kinetic energy does it have? Well, here's what we have to be able to apply. What you have to be able to apply is hopefully what you saw in the lab, and that as long as we're dealing with an ideal case, and let's here make this claim. Let's assume no friction or air resistance or anything like that, any of those yucky things. Let's call this a perfect world. Well, the one thing we can say for sure now is that the amount of mechanical energy that this thing had before is the same amount that it has now. That's the big deal. And therefore, how much kinetic energy does it have now? Well, apparently, if it has this much mechanical energy and no GPE, no gravitational potential energy, it must have, well, this much kinetic energy. or what we're saying here, is that from top to bottom, all of this gravitational potential energy has been converted into kinetic energy. At some other place, here, where this object now is moving at some speed v, I don't know, let's call this v bottom and v other, where v other is less than vb because it's on the way back up. Well, what's the one thing we can say for sure, this should still be energy, right? Yeah, of course it should. Energy. This is energy. And we can keep these guys, clone, 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 put these down here. The only thing we can say for sure now is that this still remains constant, the total amount of mechanical energy. Again, assuming none of those inconvenient factors like friction and air resistance. So now what? Well, arbitrarily, I don't know exactly what percentage of the energy is kinetic and what percent is potential, but what we do know is that the sum of these has to be the same thing. So arbitrarily, well, here's what I do know, I'll tell you the truth. Look, this thing is now at this height, which is supposed to be, I think if we do it carefully, it really is a little less than halfway. It's, I cheated there, but it's less than, it's below the halfway point. Here's what I mean by that. Let's just get rid of this. Half height is about here, and I'd say this thing is below that. You buy it? So what that means is, well, at half the height, it would have half the GPE. Does that make sense? Because GPE is MGH. So if we're at half the original height, it would have half the original GPE. But it's below the halfway height point. So, I don't know, here's half. I'm going to go a little bit below that for GPE. So now it's got, say, this much GPE. But the amount of KE it has must be the rest of the mechanical energy. So that's, well, it's, yeah, I don't know, it's like this much. Right, or if I did this right, these, oh boy, I didn't do it right, but these two, yeah, pretty good. Those two add up, the kinetic and the gravitational potential add up to the total mechanical. Okay, so these could be any mix, right? It could be, this could be bigger, and this could be smaller, oh gosh, right? As long as they still add up to the total mechanical. I like that a little better. How's that? Okay, so when we go from bottom to other, well, it looks like this kinetic has turned into some GPE, but there's still some kinetic. All right, so there can certainly be transformations like this where one kind of energy turns all the way into another, or it could be that there's still some of the original and some other transformation happening. Okay, but the big deal here is it shows us this. I mean, you only looked at two instants, top and bottom, but what you should have seen, at least in some cases, in some trials, is that the total amount of mechanical energy stays constant. Okay? All right. So let's look at a little different case, and again, we'll neglect something, like air resistance, let's say, and let's look at a 2.5 kilogram block held 15 meters above the ground. Calculate total mechanical energy. Okay, so mechanical energy, by definition, the sum of GPE and KE. All right, held, that's going to tell me that goes. Right? So it says that, well, ME is just GPE, which is just MGH. Yeah? Okay, so that means that this is just 2.5 times 9.8 times 15 meters, and we get that the total mechanical energy, it's really just the gravitational potential energy is 2.5 times 9.8 times 15 equals 367.5 joules. It's okay? All right, now the block is released and it falls to the ground. It's total mechanical energy just before it hits. Okay, now, well, again, we're going to do ME is KE plus GPE. Wait, I thought it was GPE plus KE. It doesn't matter which order you add things in. Just before it hits the ground means that goes, right? It means that it's at the smallest possible distance above height 0. Just, it's at height 0. So that means we want to do that. Well, the mechanical energy now is kinetic energy, which is 1/2 mv squared. All right, but the question is, so here's where we need the kinematics thing. How fast is it going? Oh, well, luckily, let's see. There's actually a equation that says v squared is v naught squared plus 2g delta y, or delta x, right? So we can actually just, and notice we want v squared, which is good. So that's 2 times 9.8, well, really 9.8 downward, and also 15 meters downward. So those both have the same sign, the 9.8 and the 15. So I'll leave them both positive. So v squared, it's actually, there's no real reason to find v and then just to go and square it again. So I'm just going to leave it as v squared 294. And that's actually meters squared per second squared, because it's v squared. So that means that mechanical energy is 1/2 times 2.5 kilograms times 294. Sorry about this. And let's see, so 294 times 0.5 times 2.5. Oh, imagine that. Mechanical energy is 367.5 joules. Coincidence? No, not at all. Notice, a constant amount of mechanical energy. Okay? Now again, we looked at a case where initially all the energy was gravitational potential energy, and finally, in the second instant we chose, all the mechanical energy was now kinetic energy. And in those cases, certainly there's a constant amount of mechanical energy. We sort of asked you to assume that's the case here, even though we never looked at this instant, some arbitrary instant that's not top or bottom. All right, but we can look at any instant we want, right? Here's a bullet fired straight up, and again, let's look at total mechanical energies. So here's an initial instant. This thing has a speed v naught and a mass m. All right, well, and let's say it's at what I decide to call height 0 at the very beginning. So the total mechanical energy in the beginning, the sum of GPE and KE, it's at height 0. Adios. So the mechanical energy, the total mechanical energy in the beginning is just 1/2 mv naught squared. Right? That's the kinetic energy. I'm not going to do numbers. That's an expression for this object's total mechanical energy. And I might even say its total initial mechanical energy. Right? Maybe we'd say this. That initial mechanical energy is the sum of the initial GPE and KE. Let's look at some other instant later. And let's say that this thing, is now, let's say that this bullet is now here, and now moving at this speed v. Not at the top. Clearly, it's not at the top. It's still moving upward. All right, well now we'd say that ME final is GPE final plus KE final, and ME final is MGH final plus 1/2 MV final squared. So, to tell you the truth, it's a real pain with College Board / AP that usually now we go to initial as opposed to naught. Right? So we can make that massive paradigm shift. That would be good. So let's see. MGH. All right, so the question is, what's V final squared? Oh, well, we have this expression for V final squared, remember? V final squared is V naught squared plus 2GH, right? Oh, sorry, plus 2G delta Y, right? Except for the fact that, well, G this way, delta Y this way, right? So I'm actually going to write it now as minus 2G delta Y. Oh, wait, except delta Y is really some height h. It's gotten to some height h. Nice thing about h is that gets more, oh yeah, there's an h, right? We like h's. H final, no less. So you okay with a minus here? I mean, VF has to be smaller than VI. And that's, it comes from the fact that G is, well, in this case, we wouldn't write G as negative 9.8. We just write G as 9.8. All right, and we can account for the fact that the object slows down with that negative sign. So here's what we end up with. We put all this stuff in there for V final squared. Right? And we get that the final mechanical energy is mgh final plus 1/2 m, really m, red bracket, green text, vi squared, whoops, minus 2gh final, red bracket. Now, what does that leave us with? It says mechanical final is mgh final plus 1/2 m, I'll distribute 1/2 mv initial squared, minus, look, 1/2 m times that stuff, which is just mgh final. And what does this simplify to? Look, we got an mgh final minus an mgh final. Bye. And look at this. The final mechanical energy at some other arbitrary instant comes out to be the same exact thing as the initial mechanical energy. Coincidence? Absolutely not. Okay? So, what are we to conclude here, people? Well, we are to conclude that, first of all, we have to qualify this. When only the force of gravity acts, and not things like air resistance, and not things like friction. Well, what can you conclude? I don't know. Pause for a minute. Think about it. Try to write a nice, pretty phrase about what you can conclude. Welcome back. You didn't pause. Come on, pause. Do it. All right, you're back. So, what can you conclude? You can conclude that mechanical energy is conserved when only the conservative force of gravity acts. Gravity is a force, or the force of gravity is a force, I guess, I don't know. But that force is called a conservative force because when it acts on objects, and when only it acts on objects, their mechanical energy is conserved. Therefore, gravity is called a conservative force, or the force of gravity is a conservative one. All right? So, yeah, when we're saying there's only conservative forces, mechanical energy is conserved. Or we can say in a simple mathematical expression that initial mechanical energy and final mechanical energy at any two instants you choose have to be equivalent. Now, even with non-conservative forces, total energy always conserves. There's always a constant amount of total energy in the universe, right? So even if there's friction or air resistance acting on an object or a system, well, there's always a constant amount of total energy. If we only are talking about the mechanical part of it, then we have to get rid of the frictions and the air resistances. You have to ask yourself, what is it that friction and air resistance can in many cases turn mechanical energy into that we could still make this total amount of energy be constant if we do include friction and air resistance? That's the, I mean, some of you just probably know that, but the question again is, if some mechanical energy really does disappear, if there are these non-conservative forces, then what does mechanical energy turn into? I'm going to write that down here and ask you to ponder, consider, and maybe come up with an idea. So I'll say here, what can ME transform into if it's, you know, if there are non-conservative forces? And here's a hint, it has to be a kind of energy. Mechanical energy can't turn into, say, something that's not an energy. All right, it must turn into some other kind of energy. The question is, what kind of energy could mechanical energy transform into? But we're going to focus for a little bit at least on applying this idea that as long as we can, if we agree to neglect, which we do, which we have been for a long time, neglecting things like friction and air resistance, let's see how we can apply conservation of mechanical energy. Okay? Okay, a pendulum released from rest 1.4 meters above the ground. And we want its velocity at this location, which is, here's height 0.25 meters above the ground. Here's height 1.4 meters above the ground. We want its velocity at that lowest point. Oh, look, neglect all non-conservative forces. All right, so that means that we can apply the following. If we neglect all non-conservative forces, mechanical energy is conserved. There is a constant amount of mechanical energy. And, well, typically I then go to this step. Well, mechanical energy is the sum of G, P, E, and K, E. And now here, is where we can apply the luxury of choice. The study loves his luxuries, does he not, people? He loves his algebraic luxuries. Well, I now give you the luxury of choice. And the choice we can make is told us some heights relative to the floor, but what I would rather say is, why don't I pick a different zero height that makes this question maybe a touch more convenient. And what it makes a bunch of sense to do is say, you know what, forget that. Why don't we call this height 0? So we take this down from 0.25 to 0. Well, then we got to take this down from 1.4 to 1.15 meters. Notice the important part is what it ends up being is the difference in height. This height initial is, well, 1.15 meters above this height final. That's what's important, is the difference. All right, so I think, you know, when you can, pick the lowest point as height 0. Because here's what that does. Well, it allows us, if height final is 0, that means GPE final is 0. Here's another nice thing. Released from rest, that's an algebraic luxury, isn't it? That 1/2 mv initial squared is 0. So here's a case where GPE initial, here's where I now write this as mgh initial, turns entirely into this 1/2 mv final squared. Algebraic luxury. That's not an algebraic luxury, that's just whatever. Enough of that stuff. What's the speed? Well, the speed is the, v squared, right, is 2gh initial. Recognize that? Hopefully you should. It's the same as a kinematics equation. Okay? And what do you get? You plug in and solve, and you get a 2 times 9.8 times 1.15, 4 point. Okay? Fair enough? No, right? Here's another application here, roller coaster. Now notice, folks, just notice, you're not given mass because you don't need it. Divides out of each side. All right. If I were to ask you what the energy was at some place, you would need the mass. Right? Energies have an m in them, but I didn't ask for an energy, I asked for a speed. All right. Roller coaster car moving at 8.5 at this location. So this thing has a non-zero initial velocity. This instant, well, let's say here's our final instant right here. And I don't know, let's say this is h, and this is h plus 10 meters, and this is h plus 13 meters. So maybe they give you this as 0 and 10 and 13. I mean, or you could call this height, maybe if we're talking above sea level, this is 20 meters, and this is 30 meters, and this is 33 meters. No. No. I'm still doing it. But what matters is heights relative to each other, or differences in height. So what I would say, the reason I'm doing this one is because in cases like this where an object, you know, follows this path, what people will do sometimes is say, well, I have to go first top to bottom, and then I've got to go bottom to this different new top. You don't have to do that. You can do these in one simple step, and it doesn't matter what path something follows. What matters is where it starts and where it ends. So what I would do is call this, here's height 0, here's height is 3 meters. Those are the two instants I'm looking at. I don't care what it did between those two instants. Well, again, if we're saying let's apply conservation, that assumes that, well, we were just saying mechanical energy is conserved. So this is GPE initial plus KE initial is GPE final plus KE final. Now, well, this does not go away, right? It has a non-zero initial velocity. However, we've chosen a nice final height, which does make our final GPE go away. And the rest stays. So now we can say, let's see, this is mgh initial plus 1/2 mv initial squared equals, whoops, yep, fine, 1/2 mv final squared. And, well, there's a mass in every term. There is not a 1/2 in every term. The 1/2s do not divide away. However, if we want to isolate v on the right, what you can do is multiply every term by 2. And so what you get is 2 gh initial plus 2 times 1/2 v initial squared. That's just v initial squared. Equals v final squared. Hey, that looks like a kinematics equation. No kidding. We want v final. We do that. Okay? Just use positive 9.8. Okay? The equation, what you solve for, the algebra you do will take care of things speeding up or slowing down. Okay? So we can just use positive 9.8. And I guess maybe that's because, yeah, I don't know. It also has to do with the forget it. Okay. Just trust me. Use positive 9.8 all the time, every time. Okay, so in this one, you get what you get. You solve. Okay? So, you're going to get some exposure to questions where you use this concept. Surprise, surprise, they end up looking like kinematics questions, at least for the time being. When I give you a quiz on this stuff, what I will say is use conservation of energy or use energy principles. So if you just start with a kinematics equation, not full credit. And the reason that is because when we get to cases where mechanical energy is not conserved, because there are non-conservative forces, you can't just use kinematics. All right, so we want you to get exposure and practice with using conservation of mechanical energy, and we'll get you that practice next time I see you. Okay? Okay. Farewell.